Okay, just one more. We are going to get one more of these flux integrals by using the divergence theorem. Just like before, we will calculate the divergence of f at the start. The divergence of f is partial p partial x plus partial q partial y plus partial r partial z. So let's get those. The derivative of the first part with respect to x is going to be 12x squared z. The derivative of the second part with respect to y will be 12y squared z. And the derivative of the last part is going to be 12z cubed. Now, for reasons that will become obvious in a minute, I'm going to prefer to write that as 12z squared times z, which of course is the same as z cubed, but it makes it clearer that this follows a certain pattern. What I'm going to do is factor out a 12z so that on the inside I have an x squared plus y squared plus z squared. The reason I want to do that is that S is a sphere that's centered at the origin. So this highly suggests that we're going to be converting into spherical coordinates in order to get this integral. And if we're in spherical coordinates, then this right here is rho, which is super good news. So let's set up the integral. It is the integral of this with respect to a volume differential. And now we can see that we want to convert this into spherical coordinates. So hang on just a second. Let me go and grab the conversion formulas. Those would be x equals, and you can figure these out on the go as well, but you don't always want to do that. These right here are r, so you can really base it on polar coordinates, at least for x and y. And this will be rho cosine of phi. Moreover, for the volume differential, this is going to be rho squared sine of phi d rho d phi d theta. So we have to convert the integrand into something in terms of rho, phi, and theta. And also remember, just like with the polar integral, you have to have the r dr d theta. We need to put that rho squared sine phi in. Okay, so 12z times x squared plus y squared plus z squared is really just begging to be put into spherical coordinates. 12z is 12 times rho cosine phi, and x squared plus y squared plus z squared is rho squared, right? Because after all, rho is the distance from the origin. Square it, square the distance formula like Pythagorean theorem style, and you get rho squared. So this will be equal to 12 rho to the third cosine of phi. And then divergence of f dv, meaning that this is going to turn into rho squared sine phi, will be 12 rho to the fifth power times cosine phi sine phi. We're going to make the usual substitution we make when we have cosine phi sine phi, which is that that's equal to 1/2 sine of 2 phi. 1/2 times 12 is 6. So this becomes 6 rho to the fifth sine of 2 phi. Okay, now what are our bounds of integration? This is where spherical coordinates really shine, because it's an integral over a sphere with radius r and center at the origin. That means that, I'll draw it up here actually. This means that rho is going to go from 0 up to this capital R. Phi has to cover the entire sphere, so it goes over its entire range. Likewise, theta goes over its entire range. So this right here, that is going to be our bounds of integration. So the integral is, as theta goes from 0 to 2 pi, as phi goes from 0 to pi, and as rho goes from 0 to r, of 6 rho to the 5th sine of 2 phi. That's d rho, d phi, and d theta. We'll integrate first with respect to rho, 6 rho to the 5th. This is like custom made because rho to the 6th over 6 times 6, it's going to be rho to the 6th. So it'll be rho to the 6th times sine of 2 phi. And then this is at rho equals 0 and capital R. This will be simply r to the 6th sine of 2 phi. After we do the middle integral, there won't be any variables anymore. So let's integrate this with respect to phi. The integral of sine is negative cosine. So this will be negative r to the 6th cosine of 2 phi. But then because of the chain rule, we need to divide by 2. Take a second to verify. If you take the derivative of this, negative cosine of 2 phi over 2, you'll end up multiplying by 2 and reversing the minus sign to get back your original. This will be evaluated at phi equals 0 and pi. Put in pi, negative r to the 6th cosine of 2 pi, all over 2, minus a minus, which is a plus r to the 6th cosine of 0 over 2. And cosine of 2 pi and cosine of 0 are the same thing. And actually, we kind of should have been able to see that this was going to happen because look at the function we're integrating. This is the result of the innermost integration. When you integrate a periodic function over its entire period, the result of that has to be 0 because it waves up above the x-axis exactly as much as it waves below. So the integral of this over a period will be 0. The reason I'm talking about this is that this ends up being negative r to the 6th over 2 plus r to the 6th over 2. And guess what? Those end up canceling out. So we don't even have to do the outer integral. I mean, if you want, you can say integral from 0 to 2 pi of 0 with respect to theta, but that's of course 0. And so the entire integral is 0. But if you tried to verify this using the definition of a surface integral, you'd be working on it for a month, whereas with the divergence theorem, you can get this much, much more quickly. And that is the very last problem that we will do in this series of videos. So thank you so much for sticking with me. You've been awesome. Go and keep on learning for the rest of your life.